Hello again, and welcome back to The New Creationist. Today we're going to be looking at another comparative analysis, cross-species, from most similar to human to least similar to human. Only this time we're looking at insulin. And we have the uniprot protein identifiers here in this column. 110 amino acids for the human insulin protein. And the very first thing you're going to notice, this time I've got a little chart over here on this side where I'm calculating mutations per million years according to an evolutionary time scale. And I'm calculating genetic distance in years and years per mutation in this column here. We get to play around with the numbers here. For example, if we're looking at chimp, in this case, at 2 mutations, the consensus, well, I'm not even sure there is a consensus exactly, but years for the most recent common ancestor would be 6 million, which is what I hear mostly. Sometimes, they say they give a range between 5 and 7 million years. But anyway, personally, I don't believe in these million years deep time for quite a few reasons that we'll get into in other videos. But just as we analyze and critique evolution, we're going to use this just to see how it works. Now, when you look at the table that I have set up here, the first thing you're going to notice is that human and gorilla, that gorilla is exactly identical to human at 100% similarity to human, and the very next one up on similarity to human is the Bornean orangutan, with 1 mutation between human and orangutan, and at 2 mutations difference, or 2 amino acid differences, that is, chimp is next. So chimp is actually less similar to human than either orangutan or gorilla. And chimp is as similar to human at 2 amino acid differences as macaque, the crab-eating macaque. So right off the bat, there's a little bit of a problem. Obviously, if chimpanzee were the closest, had the closest common ancestor with human, then it should be more similar. But in this case, it's not. So then we have green monkey with 3 differences in the amino acid chain. And what I've done basically is, for each mutation that affects the amino acid chain, we can put the number of mutations here. So let's say, if we were to say the most recent common ancestor between human and orangutan is 16 million years, and there were 1 mutation, whoops, so let's say there were 1 mutation in 16 million years, that would be 0.03 mutations per million years. It's also going to change all the numbers here, of course, since human and gorilla are identical. According to the calculated most recent common ancestor, they would be most recent. Next, of course, orangutan, chimpanzee, and we have calculated the distance, the genetic distance basically to a common ancestor or between species, according to evolution, where if, let's say, between human and chimp, if you have 6 million years to a common ancestor, then there's 12 million years distance. So then you take the number of mutations in 12 million years, and then you see how many mutations would occur per million years, and that's how I get this number over here. So it would be 12 million, or 2 mutations in 12 million years is going to give you 0.03125. Okay, so as we go down the list, then if you do that calculation in order to get per mutation, how many years per mutation, you would get most recent common ancestor between human and green monkey at 48 million years ago, which already, and give or take a few million years. But what you notice as you start going down the list, because the next one at 12 amino acid differences is ground squirrel, and at 13 amino acid differences is dog. Then your numbers start getting away as far as the most recent common ancestor, because now you're showing 208 million years ago where dog and human would have had a common ancestor, which is certainly I'm pretty sure is out of line with whatever they're going to come up with for common ancestry, a time span. But as we go down the list, we have more problems. Night monkey, for example, with 16 amino acid differences between human and night monkey, is going to give you a calculated most recent common ancestor at 256 million years ago, which is another problem. Of course, the other question is, why would a ground squirrel be more similar to human than a night monkey is to human? Seeing that a ground squirrel has 12 differences in the insulin chain and between human, and night monkey has 16 differences. So the percent of similarity for a night monkey at 85%, and a ground squirrel is 89% similar. Dog also. So we're seeing the same problem we saw with the cytochrome B, and a similar problem that we saw with cytochrome C. Let's keep looking. Pig and night monkey, both with 16 differences, both weighing in at 85.45% similarity to human, and hence the equidistance problem again. Why would a night monkey be equidistant to human with pig? Or in other words, why would human be equidistant to both night monkey and pig when night monkey is the primate? Did I say that right? I think you can follow me. Alright, next down, rabbit at 17 differences, cat at 21 differences, cow at 22 differences, sheep at 23 differences. And then as you calculate most recent common ancestor based on the time frame, we start getting guinea pig common ancestry between human and guinea pig would be 544 million years. Yeah, well, that's not right. Then horse at 37 differences, chicken at 40 differences in the insulin chain. Then you have carp, a fish of course, at 61 differences, a goat at 63 differences in the insulin chain, and all these are manually curated in Uniprot. So they've already been checked and verified manually. So we have chicken, more similar to human, and chicken's of course a bird, than a goat, which is a mammal, or a camel, which is also a mammal. So why would a carp be more similar to human than a goat is to human? And of course, you definitely see where the calculated most recent common ancestor is getting way out of hand. Then we keep on down the list here for squirrel monkey, which is a mammal, with a whopping 64 differences between squirrel monkey and human. Percent of similarity is 41.82%. So the evolutionary brain crushing question is, why in the world would a carp be more similar to human than a squirrel monkey, which is a primate? Now let's keep on going. So you've got a zebrafish, which of course is a fish, with exactly the same number of differences at 64 as a squirrel monkey, the same exact percentage of identity, percentage of similarity. So a squirrel monkey and a zebrafish are as both equally as similar to human, and I just kind of have to chuckle at how, in light of the evidence, how in the world could anyone who knows it, in other words, you learned it in college, you learned it in school, you believed it because that's what you were taught and you trusted your teachers. Fine. Look at the evidence for yourself, and then you start seeing discrepancies. What the question then is, the higher question is, the people that actually compile this evidence for a living, why don't they present this? Why don't they look at the evidence and actually open their eyes? I don't get it. If there's different, you can make a mistake. You can say, well, somebody's told me this and I believed it because I went to school, and why would they teach me wrong? Well, maybe they didn't know. Maybe it was a mistake. It's time to correct the mistake. The mistake is evolution. Thanks, and hope that was enlightening, and hope to see you next time. Until then, God bless.